I welcome all of you to this seminar from Professor Pascal Bellon from the University of Illinois at Urbana-Champaign. As evident from his CV, he is a master of many trades. His expertise ranges from experimentation, including the nanoscale characterization, transmission electron microscopy, the APT, and also numerous modeling methods, including atomistic and continuum. So, and he happens to be also working in one of the areas which I work on, which is phase field modeling. So Professor Bellon is a Hammer Professor in the Department of Material Science and Engineering at Illinois. Previously, he has had positions in France, and in 1996, he joined the Department of Science and Engineering at the University of Illinois at Urbana-Champaign. And the numerous awards that he has won include the NSF Career Award in 1998, the Racial Faculty Scholar in 2012, and he was also inducted as a Hammer Professor starting 2016. He has also been an interim department head in MSc at Illinois in 2019. So, Pascal, we are very delighted to have you here, extremely honored. The floor is all yours.
Well, thank you very much, Ankit, and for this kind introduction and for the invitation to give this presentation and share with you and your audience some of our research results on self-organized alloy microstructures for extreme environments. One of the main kind of environments that we have studied at Illinois is the case of alloys exposed to or subjected to radiation by energetic particles. So we'll start my talk with some brief introductory material on radiation effects in metallic alloys, and then I'll move in the second point to what are those self-organization reactions and how they lead to the stabilization of nanostructures. In the following point in part 3, I'll give you also an illustration of some of the results that are similar that that we have obtained in alloys subjected to severe plastic deformation, and then I'll conclude and provide some perspectives on the research I would have presented. Here on this slide, you see a picture of past and current members of the group. This is taken at TMS in San Diego 2 years ago, and all the students with the blue name are current student members, and all the people in this picture have more or less been involved with part of the research that I'm presenting today. But also, I want to stress that all this work has been done in very close collaboration with my colleague Bob Averback, who's a faculty also at Illinois, and we have been collaborating together for over 20 years, and in large part, really, it's the results that were presented today are a summary or an overview of some of the key results that Bob and I have obtained with our students and postdocs over the years. So starting with this brief review of radiation effects in metals. Here, the reason why we're interested in materials under radiations is that for advanced nuclear reactors and more safer also power generation through nuclear energy, there is a need to develop materials that are resistant to very high level of radiation damage and can operate at a high temperature. And this is challenging for the following reasons. And so when an energetic particle zips through a metallic target, as a function, depending upon its charge, its mass, its incident energy, the flux, and the temperature, certain amounts of damage defects are created. But here we're concerned with metallic materials, and so this energetic particle will start first by excite the electronic system of the elements or the atoms in the target, but these excitations do not lead to any defect. It is in the second phase of during which the incoming particle undergo nuclear interactions or interactions with the nuclei of the atoms in the target that damage can be produced, and that damage takes place typically by the formation of so-called displacement cascades, which extend over a few nanometers, last a few picoseconds, and results in the formation of Frankel pairs, that is a vacancy in an interstitial There is also a metric or measure of the damage under radiation. So a displacement is one pair of vacancy in self-interstitial, and the measure of the damage would be whenever you have created one pair for each atom in the material. So 1 dPa is a very high level of damage already. It means you have created on every lattice side a vacancy or an interstitial during the duration of the irradiation. The irradiation rate or damage rate, dPa per second, is also important, as we'll see. In addition to creating damage, irradiation also creates forced chemical mixing during this very energetic displacement cascade. Atoms are forced to move around. Professor Bob Averbach derived, in fact, a picture that you could in many ways think of this displacement cascade as a high or superheated liquid that exists in for again a picosecond or so, and that can lead to forced chemical mixing, just like as if you were bringing the system to very high temperature. This point defects and the mixing lead to potential damage. The most beneficial thing would be for those to recombine, and then interstitials and vacancies would disappear. But in reality, they do not, or not all of them do. So some of the point defects may cluster and form dislocation loops, which may, under applied stress, climb and contribute to creep. Other point defects may co-cluster with helium atoms and form bubbles which may contribute to embrittlement. Then point defects, also vacancies, may clusters and form voids, leading to swelling. And in addition, and it's going to be relevant to part of the talk here, radiation sets up permanent fluxes in these microstructures, irradiated microstructures. And the reason is that defects are produced homogeneously, but they eliminate at localized sinks, such as grain boundaries or dislocation lines. And so there is a permanent, under steady stationary irradiation, there are permanent defect fluxes that are produced coming from the homogeneous production within the grains to the elimination of these point defects on sinks. And in some cases, these point defect fluxes may couple with solute fluxes, leading to radiation-induced segregation and in some cases precipitation. You may see from this slide here that the main cause of this, a lot of these damages here, types of damage, is the long-range migration of vacancies and interstitials, and sometimes alloying element. So there are two broad strategies to improve radiation resistance. One is to slow down point defects. If we slow down point defects, we will increase their concentration, and the recombination rate is proportional to the concentration of interstitials and vacancies. So when these concentrations are high, the recombination rate is high, and this is beneficial. One option to achieve this, this goal is to use solute that would trap point defects and thus slow down their kinetics. There are some examples that have been demonstrated in the 70s and here in the 1990s by Kato and his co-workers, where they added oversized impurities such as zirconium, hafnium in 316 stainless steel, and demonstrated using 1 MeV electron irradiation here is that in those materials doped with impurities, the traditional radiation damage of chromium depletion at a grain boundary here in a standard 316 stainless steel is eliminated, or this chromium depletion is does not take place if one has doped the material with these impurities that hopefully trap point defects. It's complicated because that effect is only transient; it fades away. And there's been some, so we worked recently in some on that point, and I'm not going to have time to present those results, but we have two papers that came from the PhD thesis of Craig Daniels and in our group that looking at a better atomistic understanding of this strategy and how one can use materials data such as extensive diffusion database to screen and select the most effective solutes here using a rational design. This also approach is sometimes has been recently considered as a potential strategy for high entropy alloys, where there's been some report that the high entropy or the disorder that exists in a high entropy alloy can slow down point defects and promote recombination and thus radiation resistance. It's still, there is an active ongoing discussion as to whether this is really the reason as to why high entropy alloys may have good radiation resistance, and I'll simply point you to the references listed at the bottom of the page here. So the second strategy is, instead of relying on recombination, is to rely on interfaces, with this idea that interfaces will trap vacancies, interstitials, helium atoms, and promote recombination or the annihilation of those point defects. I illustrated here two implementations of this strategy. One where one would introduce a high number density of very small oxide precipitates in a steel. So these are known as nano-ODS steels, and these the interface between the oxide nanoprecipitates and the matrix seem to be very effective sinks for point defects, and so these are attractive materials. Another approach that in fact was heavily studied at Los Alamos in last, say, for about 10 or 15 years is to rely on nano-layered composites. Here's an example of copper niobium nano-layer. And thanks to the very high number density of interfaces, when you have a displacement cascade here, close to a copper niobium interface, you may resolve or eliminate all the damage right away and not have to worry about its accumulation over time. One of the challenges, however, with these nanostructured materials is that nanostructures tend to be prone to coarsening, especially at elevated temperature and possibly under radiating conditions. And so at Illinois with Bob Effenberg, we have targeted a different approach, which is to rely on self-organization reactions to stabilize nanostructures under irradiation. And now this will be the main focus of my presentation today. And so to illustrate what we mean by self-organization, here's one of the first demonstrated example of self-organization in an irradiated alloy. That's from the work of Nelson and co-workers. You can see it's a 50-year-old already, so it's not very recent, but nevertheless, there's a lot of intriguing science around it, as I will show you. So in this case, this is a gamma-gamma prime alloy. So we have in bright field here, in bright contrast, in dark field mode, this gamma prime precipitates in a nickel-based alloy. And these precipitates have been prepared by the appropriate heat treatment. And if you irradiate this material at the right temperature, that is not too high, not too low, the precipitates will tend to decrease over time due to the irradiation damage and the mixing that I mentioned earlier on. But as you increase the dose, and this is going from top right to bottom left to bottom right, the microstructure seems to reach a steady state microstructure that is independent of the initial state. So here they started this set of experiment with pre-existing gamma prime precipitates. If you were to start from a solid solution, they reported that they obtained the same microstructure. And so it seems that under those conditions, under radiation, the microstructure or the precipitates reach a finite but stable steady state size. And this is what I'm going to now detail in this section too. So here are more examples of self-organization reactions in irradiated materials. On the left-hand side, you have a void superlattice that is formed in irradiated niobium. In the middle, you have walls of dislocation loops and dislocations that formed in pure copper under radiation. On the right-hand side, this is an alloy, which is what we are going to focus in this presentation on, of here nickel and silicon. Again, silicon-rich regions from this those gamma prime precipitates. And here you can see that here again, there is sort of a finite size for those precipitates, and even seems that they are formed an ordered array of precipitates at the scale of tens of nanometers. And so one of the fundamental questions that we set out to study is why do materials and alloys here self-organize on their radiation? The second question was whether we could use this self-organization to tailor and enhance radiation resistance. And these are largely the questions that we're going to use to investigate today and see whether self-organization can be used to obtain materials that would be resistant to these extreme environments by design. So, and there is this analogy also with self-organization in equilibrium systems. And there's this question as to whether some of the knowledge has been developed over the years over patterning and self-organization of microstructures in, for instance, in systems such as these magnetic materials or in other systems that I might mention along the way. Could these whether those concepts used for equilibrium systems could be also used for non-equilibrium systems such as alloys under radiations? So we want to focus on an alloy that has precipitates, and picking up from this brief description of radiation damage in alloys, imagine that here we have an incoming projectile that has created this displacement cascade extending over a few nanometers, lasting a picosecond or two. In that displacement cascade, atoms, as I mentioned, will be forced to relocate from their initial position to a nearby location. The relocation distance R varies from an angstrom to a nanometer roughly. And if I have a precipitate that's, for simplicity, assume here to be pure B or pure solute precipitate, some of these relocation events here as process one, some of these solute atoms would be relocated into the matrix. So it's going to contribute to the dissolution of the precipitate. In that displacement cascade, if you think about it as a hot liquid for a picosecond, as I mentioned earlier, this process here may lead to also redistribution of the atoms, sometimes maybe inducing dissolution if the material is somewhat low or reasonable intermediate heat of mixing. In very reactive system, it may favor the precipitation, as we'll see later. And then there's a third process which will always promote growth, which is the thermally activated transport of solute atoms back to the precipitate. And here we are envisioning a situation where we are operating under conditions such as at equilibrium, the system would, due to its thermodynamic nature, would want to form stable precipitates. So we have these three processes, medium range ballistic germs, short range germs, and thermal germs. And in moderately miscible alloy system, so the mechanisms 1 and 2 lead to dissolution, and the mechanism 3 to coarsening or renucleation and precipitation. So there's a competition between these mechanisms. In highly reactive systems, even in the absence of thermally activated migration, we'll see that just 1 and 2 can compete with one another, and this is important for self-organization. So this, I want just to revisit briefly this idea of competing dynamic processes, because it's essential to the reason why these alloys self-organize. So we have these processes 1 and 2, let's say, that would contribute to dissolution, and 3 to the growth of these precipitates. There are simple models that can be written down describing the expected dissolution rate, growth rate of those precipitates as a function of the jump frequencies of atoms in the matrix. So here, thermally activated jump frequency. Their jump distance for those diffusion is 1 nearest neighbor distance. In contrast, this forced mixing, which we tend to call ballistic mixing, following the nomenclature introduced by Georges Martin. So this ballistic mixing takes place at the different jump frequency, which is related to the displacement rate or the damage rate. And the range of these relocation events or replacement events now is larger. It ranges from 1 to 10 years near the distance. And the main way that we know about this distribution of relocation distances is from molecular dynamic simulations. And here's an example of the histogram of relocation distances. This is a normalized histogram here as a function of distance. This is a semi-log plot. And so what you see is that here for various irradiation conditions in this copper-silver alloy, we see an exponential tail of mixing. And this is this kind of a medium range mixing that is very unique to irradiation here. And there is a little bit of this also short range or jumps from one location to a nearest neighbor site. And this is this process labeled number 2. So we can, so what I want to stress upon you is, or impress upon you, is the fact that there are a lot of parameters that control the evolution of the systems, but there are 2 key reduced parameters that capture this competition between thermal diffusion and ballistic mixing. One is a relative rate of mixing over thermal diffusion. So when the relative rate is high, we are promoting mixing at the expense of thermal relaxation or precipitate growth. But so it's a competition through rates, but it is also essential to realize that there's a competition of these processes through their distinct length scales. So the mixing has an intrinsic length scale R that can be several times larger than the intrinsic length scale of thermal diffusion lambda. And then when we model the evolution of an AB alloy or model alloy using phase field modeling or kinetic Monte Carlo simulations, I'll show you some illustrations later. What we found is that we can build a phase diagram of the steady states that the alloy would reach under radiation. And here we kept temperature and composition constant. But in addition to those 2 axes, which would be the only ones we would see in an equilibrium phase diagram, here in this steady state phase diagram, we also have this forcing intensity, which is this related, the rate of ballistic jump frequency over thermal jump frequency. And along the vertical axis, we have this mean ballistic relocation distance. Here it's normalized by the nearest neighbor distance, so it's R over lambda from my previous slide. And so what we see is that when R in these reduced units is small, we are the 2 steady states we are left with are, so to speak, trivial steady states. When the forcing is small, when gamma is small, this is a system that remains close to its equilibrium state. It is here in the state of macroscopic phase separation. When you increase the ballistic jump frequency, you can force the system, and the mixing now becomes so dominant that thermal diffusion cannot keep up with that forced mixing, and the system ends up in a steady state that's a solid solution. What's intriguing, and it was not realized at the time here when Raul Enrique did his PhD work here at Illinois, is that there is a critical length scale, RC, or relocation distance, above which a new steady state regime opens up, where material spontaneously would want to stabilize itself in a steady state that is nanostructured, as illustrated by these KMC simulations here. So after obtaining these results with the experimental validation, and so what we did is that we varied, so we picked an alloy system, an ion, so that R is fixed. And the simplest thing to do in experiment is to increase the irradiation temperature. When we increase the irradiation temperature at very low temperature, so thermal diffusion is very low, sluggish. So this reduced forcing is very high. So we'd start here on the right side. And then as we increase temperature, we increase thermal diffusion, and we expect the system to explode this dashed line. And so here's an example here for copper silver, where in the S-grown state or irradiated at room temperature, cross sections in Z contrast and STEM mode show that we have a uniform alloy, so it's a solid solution. And then as we increase the irradiation temperature from room temperature to 175 to 200, we start observing the formation of precipitates in bright contrast here. And we monitored that after those, the size of these precipitates no longer changes with the dose. And here's an illustration on an alloy that's very similar, where here in bright field mode, now the silver-rich precipitates are identified through their moire pattern, those fringes here. And on the right-hand side, you have size histograms for those precipitates from a dose and a dose twice as large. And you can see that the size histogram hasn't changed at all. So to confirming the steady state nature of these nanoprecipitates. So in some ways, it's quite similar to the behavior that was that's observed in nano diasteels, where the inclusions were nano oxide precipitates, but here it's done with metallic precipitates. And in this particular case, we know that under those conditions I'm showing you here, these precipitates will never corrosion under radiation, because this is the regime where they are stable. And we know this guided by the steady state phase diagram that's on the left here. There's another type of self-organization that also can happen is, now if we take alloy systems that are highly immiscible, such as copper molybdenum, copper tungsten, the displacement cascade is such that if we thought, as I said, we can think of it as a very hot liquid for a picosecond or two. If you look at the equilibrium phase diagram of the copper molybdenum system, it is, these two elements are even immiscible in the liquid state. And so what's happening here is that in that displacement cascade, molybdenum clustering starts to take place. This is a snapshot of a molecular dynamic simulation. And on the right-hand side is the experiment showing that, again, here we can, just by irradiation at room temperature, so it's a temperature where there's no diffusion of silver. With this other mechanism, we can trigger the precipitation of very small clusters, 1 to 2 nanometers in size and diameter. And those are extremely stable because tungsten or molybdenum are refractory metals with very, very low diffusivity in copper. So here we have a second way of, if you want, tailor or structure the microstructure with a high density of very small precipitates that will be stable under radiation, and in some cases even under annealing at very high temperature. So for instance, a benefit of this dual patterning here in an alloy, but we combine both self-organization pathways, copper, silver, tungsten, we end up with 5 to 6 or 6 nanometer silver precipitates that coexist with 1 to 2 nanometer tungsten, very small clusters. And this material with a dual population of nanoprecipitates has an extreme resistance to radiation up to, say, 400 degrees Celsius. And you can see here, there's some details I'm not going to have time to discuss, but the point is that it's copper. So with small alloying additions, and that material is has a nanostructure that is stable well to pretty much or about half of its melting temperature. So a high homologous temperature for this material suddenly. So this is on the experimental side. Now what I want to share with you is a little bit of a perspective on from the modeling side, how we think of the origin of the patterning and where we can make a connection with patterning in equilibrium system. So I mentioned briefly that we use phase field modeling to build this phase diagram that I showed you previously. This phase field model is captured here by a kinetic equation that controls the evolution of one concentration field. We're in a binary alloy. So C is the concentration, say, of the B species. And we're going to, we said that we can see these material systems as systems where there are two dynamics that are competing. because of the separation in length scale and time scale, we're going to assume that the overall evolution of the concentration field can be modeled by the sum of two processes. So and for each process, we're going to use or models that are available to describe that part of the kinetics. So in green, for instance, this is the thermally activated diffusion that's responsible for phase separation in this alloy system. For that, we're going to use a traditional Cann-Hilliard free energy for an inhomogeneous system. So some of you might be familiar that in that case, we have a free energy density for the homogeneous state that is essentially a regular solution model with an interaction parameter omega and this entropic contribution. And then there is a energy penalty due to the formation of interfaces, and with this gradient energy coefficient kappa 1. And so now this is for the first dynamics. For the mixing, since the mixing takes place over a range of distances, we have to use a different model. And here we describe the mixing as a convolution product. Essentially, we're just saying the concentration at the side R decreases because we recoil this atom B elsewhere at a frequency gamma B, and atoms that were sitting at a site R prime may be recoiled to site R through that same process, but this is weighted by a distribution function for these relocation distances. And we have reasons to, from MD simulations, to use either exponential or Gaussian relocation distribution functions. And so I'm going to use a Gaussian form for simplicity in the next few slides. And so the idea is that what we've seen now is using that phase field model is that R needs to be greater than RC, or critical radius distance, to trigger self-organization. And this self-organization only takes place in a range of forcing intensity. So if you drive the system too hard, you dissolve the precipitates. If you do not drive it hard enough, the system will revert to microscopic phase separation. So you have to find this sweet spot here for patterning. How to make a connection with equilibrium system? Well, there's an approach that Georges Martin proposed in 1984 for a related case, where it said, would it be possible to combine these two different contributions into one contribution coming from, that would mimic the one we know for a thermal system, but that for an effective system. So instead of using the true free energy of the system, I'm using an effective free energy. And the question is that would be the properties of that effective free energy to capture this competition between the two processes. So in the recent papers that are listed at the bottom of this slide, what we have done is that we show that you can perform, so to speak, a Taylor expansion of this ballistic mixing term in orange. There's a somewhat nasty convolution integral into a series of differential terms for the composition field. And what's intriguing is that if you linearize the Cann-Hilliard equation, you get a similar series of terms, at least the first two terms. So for instance, here there is, the leading term here is a Laplacian, so it's fixed law. And there is a thermal part, but there's also a ballistic part, which is proportional to this driving coefficient gamma. There is the next term is one where normally we would have this gradient energy coefficient kappa 1, but here we see there's a term coming from irradiation, and there are other terms as well. And we show that it's sufficient to some extent there's a lot of useful things to learn just simply by truncating that expansion to the third term. So we refer to this as an order 3 model. And then we showed that here, essentially the effective free energy that you end up obtaining is one where there is an effective free energy density for the homogeneous state. There's an effective gradient energy coefficient kappa 1 effective, And there's a new term that's proportional to the Laplacian of C to the second power. So often this is referred to as an extended Canadian model. And for a model like this, we can calculate an effective interface energy as well. So that's the expression is given here. And the key point is that what's interesting is that when we increase gamma, you can see that this term is positive. The phase separation is driven by omega, the interaction term. When we increase gamma, we reduce, as if we were reducing the driving force for phase separation. This is how we can express or rationalize the stabilization of a solid solution. But here, when we look at the second term here, there's something intriguing is that when we increase gamma, we may also change the sign of this gradient energy coefficient. And since this is related to the interface energy, that suggests that pattern formation or can be possibly envisioned as a way, as a mechanism by which irradiation changes the sign of the effective free interface energy from positive to negative. But the model is regularized, if you want, through the introduction of the third term, which is here always positive. So I don't want to spend too much time on details because I think it's a little bit besides the point of this seminar. But we use phase field modeling in MOOS, this open platform that's been developed at Idaho National Lab to solve this phase field model. Here's the kind of microstructures we see for macroscopic phase separation, compositional patterning, or a disordered solid solution. Since we have an effective free energy, even when we have metastable states, we can decide which one is the most stable. And we built this in somewhat great depth, this steady state phase diagram that I mentioned earlier. And you recognize here in the middle this region for self-organization or compositional patterning. This was in 2D for an equiatomic composition. Here, I think I'm going to skip this point and in the interest of time. And so if one were to look at non-equiatomic composition, in fact, this effective free energy that I'm indicated or presented before is a very similar form to the Swift-Orenberg free energy that is that's been extensively used to capture pattern formation in non-equilibrium systems. And so there's, in some ways, our model provides a seamless description going from a Canyon free energy functional to one of this Swift-Orenberg functional that's really heavily used for patterning system. In real materials, when we look at their microstructures, we know that their microstructure is complex, can include grain boundaries and sakes, and as I mentioned at some point in the introduction. And so we also had an interest in looking at grain boundaries. And so here is an example of a case where under radiation of a copper tungsten thin film, tungsten precipitates become stable under radiation, and you see that they appear to have formed compositional patterns within the grains as well at grain boundaries and at triple junctions. So we recently started to extend the previous model to microstructures that contain sinks, such as grain boundaries and dislocation loops, and consider now what kind of coupling there might exist between patterning in the bulk and patterning at grain boundaries, or is it possible for these two patterning reactions to coexist? So Gabriel Bourda from who obtained his PhD at University of Lille with Ludovic Trini had developed models that can, for instance, here represent low angle or symmetric tilt grain boundaries with dislocation score represented by the elastic field and a phase field parameter that captures enforce the boundary condition for point defects around this sink. And so we apply this model to an alloy under radiation that is with this forced mixing. We picked aluminum antimony as a model system, in part because we're doing some experiments on this alloy system. It's also one where there is radiation-induced segregation that is from DFT data. We know that there is a strong binding energy between antimony and vacancy in aluminum, and that leads to flux coupling that is at low temperature. If you calculate these Onsager coefficients that are presented here using different techniques, and what you would see is that at low temperature, if I pick the blue curve or the red curve, it means that every time a vacancy reaches or moves through the microstructure, it drags with it one solute atom when this ratio is 1. And so at low temperature, there is a very effective solute drag. And Gabriel looked at microstructures of near grain boundary here with the misorientation angle of about 10 degrees. And so there are about 16 dislocations here along the grain boundary, which is runs vertically. And what is intriguing is that we observed that so while in the absence of mixing, the radiation-induced segregation would lead to the formation of a segregated film of solute at the grain boundary. When we include the mixing and with the coefficient of 25 or more mixing at value 100 or even more mixing at this, when this coefficient goes up to 250, we reduce the amount of segregation, which we expected, but at the same time, it changed the distribution of solute atoms on the grain boundary. And you can see here we went from a continuous film to 2 precipitates to 4 precipitates to a very faint continuous film. So it is another example of patterning where the system chooses its own length scale and number density of precipitates here along the grain boundary. This was in a dilute system. We've done this also in a concentrated system, and in a case where at 20% antimony here, where there is also patterning in the bulk as well as the grain boundary. And so in some ways, the facial model suggests that we can get dual compositional patterning, where we have precipitates a little that exist along the grain boundary, smaller precipitates in the bulk, and a precipitate denuded zone at the interface between the two. And we argue that in many ways it seems to mimic the microstructure that I showed you earlier. There's still ongoing work to do a more quantitative comparison and with the experiments. And okay, so I'm looking at the clock, and I have covered everything I wanted to cover for alloys under radiation. So let me briefly give you a quick flavor of self-organization of alloys under plastic deformation. It will be easy because in many ways it's for reasons that we understand now, but really surprised us originally. These alloys under severe plastic deformation exhibit a similar tendency to self-organize. And so here's an image of a nanocomposite of copper and silver synthesized by ball milling at an intermediate temperature. So just like under radiation, if you ball mill at low temperature or cryo temperature, disordering, mixing takes place and you have a solid solution. If you ball mill at too high a temperature, silver and copper phases coarsen. But here at this intermediate temperature, they reach a steady state size. And for on the right hand side, this is a more reactive system, copper niobium, where in this case the niobium precipitates in SEM in secondary electron mode shows up at dark regions. Whether we start from a solid solution or from pre-existing precipitates, using high pressure torsion, we get at very high plastic strains, we get the same number density and size of nanoprecipitates, whether the initial microstructure had precipitates or it had or not, or whether those precipitates were too big for the steady state size. And if you're interested, recently last year we published a review on patterning in systems subjected to plastic deformation in JOM, and so I would encourage you to look at this issue. And here, just to give you a flavor, and this is I don't know. I hope that okay, of what, how the self-organization proceeds. On the left-hand side, this was a bilayer structure in an FCC lattice that we model using, evolved using kinetic Monte Carlo simulations. And you can see that the A and B atoms, red and blue, started with a bilayer, but after a while that they formed a steady state solution. And if we start with a steady state solution, we get the same steady state. And so this is the case of either irradiation or severe plastic deformation at low temperature. What's more interesting is when we do that at intermediate temperature, if we start from a bilayer, you see that first there is kinetic raffling at interfaces, and then progressively we form protrusion. This protrusion may be detached from the original layers, refining the microstructure. And this microstructure is progressively refined. If we were to start with the solid solution on the right, now this structure coarsens. And but what's intriguing is that if you let them evolve long enough, they will essentially reach the same steady state, that is a microstructure or two microstructures that are statistically equivalent. And we think that this captures very well what I showed you on the ball milling, where you can see this here after zooming at a certain scale, the coexistence of copper-rich and silver-rich regions. And so here we have a self-organization or patterning on the plastic deformation. I won't have time to say that, but the reason why this self-organization takes place is that dislocations, when they shear or glide through material, it leads to what's called a super diffusive mixing. That is a concept that was introduced about 100 years ago by a British scientist, Richardson, realizing that when you have markers in the microstructure, and if you have imagined dislocations or flows shearing these markers, the larger the separation distance, the more likely it is that the pair will be sheared and the more effective the mixing is. And so, and this is the key reason for this self-organization. And we tested that super diffusive mixing is indeed taking place on the ball milling. And the last example I would quickly want to show you is going back to this copper silver system. It's a case where we have 10% silver in copper. It forms a solid solution if we ball mill at room temperature. And then we, after compaction and sintering, we anneal this material at different temperatures to reprecipitate the silver. But by choosing the annealing temperature for 1 hour, we can choose different precipitate sizes. And we tested these nanocomposites on their sliding wear using a pin-on-disc wear tester. And then what we found is was kind of intriguing and another example of self-organization. So here are images of these nanocomposites obtained by annealing at low temperature on the left or at high temperature on the right. The hardness is high, but and as you expect, the microstructure on the left has a higher hardness, slightly exceeding 5 gigapascals. When we perform the wear test, we measure the wear rates for these different alloys. They have the same composition, just a different initial microstructure. And we found that the wear rate, which is the blue or the red curves reported on the left-hand side, is lowest when the hardness is the lowest. And this is the points on the right. This is kind of surprising that low hardness would improve wear resistance. And when we look at the microstructure of these materials, what we found, and that's what you see on the right-hand side, is that the material that has a high wear resistance is one where spontaneously the copper and silver phases form a nano-layered structure. You see it from the top surface. This is a series of TM, STM micrographs through the thickness away from the wear interface. And you can see that here over microns, this material that started with aqueous silver precipitates chose to form self-organized nano layers, a little bit like phyllo dough, at the scale down to maybe 10 nanometers at the very top. And this layered structure is very good wear resistance, we think, because it provides a very good resistance to a crack propagation into the material. So it wears, but the wear debris or particles are very small, and therefore the wear rate is small. And plus, it generates beautiful microstructure, as you see on the right-hand side. So this is the end of my presentation here. So I summarized my conclusions that I believe I convinced you, hopefully, that compositional patterning under irradiation or severe plastic deformation can be seen as resulting from the competition between different dynamics that have different rates and different range and different driving forces. Here, one favoring clustering, another one dissolution. That we can understand the formation of patterns in the systems using sometimes in effective free energy concept or effective interface energies. That recently we showed that this patterning can take place at grain boundaries. That patterning can also take place in the alloys subjected to severe plastic deformation, sometimes resulting in isotropic structures, sometimes lamellar structures. And then in many cases, both for alloys under irradiation and on the severe plastic deformation, these dynamically stabilized nanostructures can offer a strong or can perform very well under extreme environments. And because they are stable, they are the steady state where the system wants to be under those extreme environments, these microstructures will not change with time. And so it is certainly an intrinsic advantage where we would have a resistance to extreme environment here by design. Thank you very much for your attention. I'll stop here and be happy to answer any question you might have.
Yeah, thank you so much, Pascal. That was an excellent talk. Very impressed, actually. So yeah, audience can go ahead and ask questions. So Pascal, if you can, we can address the questions one by one. So yeah, anyone, please. I don't see anything in the chat box. So maybe I can just go ahead and ask my question first.
Please.
Yes. So on slide 11, which showed the phase diagram.
And so here, I don't know what's happening here.
Yeah, you can probably just click on the got it button and then it should.
Yeah, I might. It seems that.
Yeah, it enabled the auto captioning, I think. Yeah.
Yeah, it's just that because I have I might want to stop sharing, but now I think I'll have to. Oh, maybe this might work. Okay, so now I have the pointer, so that's better. And now at least I should be able to go back.
Yes,
you still see.
Yeah, it's perfect. Yeah.
Slide 11.
Yes, it's perfect. Yeah.
And
so yeah, I had a question about this. So I presume this was done for 2D microstructure.
So the modeling, or
I presume that this was actually a phase diagram that was generated out of phase field and the KMC modeling approach.
So on the left hand side, those boundaries were initially obtained with a 1D, in fact, phase field model. Mm-hmm. Then, as I showed you later, we used moves to do 2D, and now we do 3D. Mm-hmm. And the KMC simulations are 3-dimensional.
Okay. Yeah. So so my question is along those lines. So because you understand how does dimensionality, the spatial dimensionality, affect these results. So what do you think is the influence of dimensionality? Like we go from 1D to 2D to 3D. Do these lines really like sort of move a little bit, or what do you see there?
Yes, yeah, as you said, you're perfectly right that the dimensionality will influence the outcome, and as we anticipate, the morphology of these steady state here will be different in 1D, 2D, and 3D. And I know that you know that, but just for the so it means you might have in a 1D system you'll only have lamellar phases. Right. In 2D you might have lamellar and tubular, and in 3D you might have lamellar tubes and spheres or isolated particles, and so that's the first big change, and in fact if one is you will miss some of these domains boundaries here. So this one particular diagram, and that's maybe why in this case there's not too much difference because it is for an equiatomic alloy. So at the 50-50 composition in those model alloy systems, the only stable phase is the laminar phase. And so whether you're in a 1D, 2D, or 3D phase field model, you'll get essentially the same results pretty much. Okay. But when we go off that equiatomic composition, then the boundaries change significantly.
Oh, I see. Yeah, yeah. Right. So my other question, so I was very actually happy and very impressed actually to see that how you have adapted the phase field crystal model for irradiation damage, and that's very impressive work, I believe. My question is really again going back to the phase field model, which is going to operate at a slightly larger length scale. Have you also tried to understand the influence of grain boundaries at the mesoscale phase separation when they're impacted by irradiation?
Yeah, so some of the results I showed here were so this is that phase field crystal model that you're referencing, and what we were surprised is that essentially the effective free energy function that we derived for a system under radiation had the same functional form as in the patterning regime as the one of a Swift or Hornberg, at least, or very similar to, in some cases with additional modes, but here it's the case where we included grain boundaries. Yes. And so this is where we try to here, and it's not obvious because this is a chemical map here, but we don't have the microstructure. This is this elongated box is a system where there is a symmetric tilt grain boundary that runs along the vertical axis in the middle of the sample.
So for this approach, you might have, so if this is a phase field model, I assume. Yes. So if this is a phase field model, then I know that the older work of Professor Abhinandan has this coupling between the compositional order parameter, which is the conserved quantity, and the non-conserved parameter.
Okay, I see. Yeah.
Of Alan Kahn, and so what happens there is that the phase segregation the phase separation when it happens, the ligaments try to sort of align sometimes along the grain boundaries, and in other cases perpendicular to the grain boundary. So how does that? I presume this model can actually capture those subtleties.
So yeah, I see. Now I better understand your question. So you're right that in this case there is no coupling between the composition field and the order parameter capturing the dislocations, but Gabriel in his thesis studied dislocation climb, and you can add a motion of the dislocation core based, in fact, on the flux of point defects feeding those dislocation core. So there's a physical, you can really physically capture the effect of, I mean, include this in a somewhat quantitative way, the origin of dislocation climb or the coupling with composition here. We have not done yet so, but this is on the wish list. Yes. There's another attempt that we did that also is where we included directly that coupling, which is using the model from Fabdi Abdeljawad and Stephen Foyles, where now the grain boundary is represented by a grain boundary phase. And that phase is captured by another parameter, just like that it discussed, that evolves with the Allen-Kahn equation. And in some cases, we couple both the conserved and non-conserved fields, and then you would see motion. Yeah, so the grain boundaries may move, drag the precipitates behind them, or the precipitate. So there are all sorts of intriguing coupled evolutions that can happen. And you're right that Professor Abhinandan and his collaborators have worked on that. Yeah.
So one final question before I let the others also chip in with any questions. So very nice work, really, because the grain boundaries is, I presume, a very important part of this. So is there any way by which we can distinguish between low angle grain boundaries and high angle? Because we do want to understand the influence of that as well, I presume, because texture does.
Yes, right. This is a very good question. We know that under irradiated alloys or microstructures, low angle and special grain boundaries behave very differently. And so, say, for instance, coherent twin boundaries, sigma 3 twin boundaries, with are poor sinks, and so they will not collect many point defects, and so segregation would be essentially very limited there, right? So whereas large angle grain boundaries are good sinks, they will collect a lot of solute in a system where radiation-induced segregation takes place, and so we expect the behaviors to be different. With this particular description here, we cannot have the dislocation core become too close to one another. Plus, we know from linear elasticity that the decomposition of a grain boundary into an array of misfitting dislocations loses its meaningfulness, right? And so beyond 10 to 15 degrees, we would not even want to try this approach, and that's why we also looked at the model from Abdeljawad and Foils.
Oh, I see. Yeah, very nice. Yeah. So I don't see any questions. So Krishna, do you have something to add to this?
Yeah, Ankit, your question spanned so much that I even almost forgot. But
I'm so sorry about that.
No.
I just got excited.
No, of course. No, this was a great talk because I think I learned a lot. Do you think we could develop some, for lack of a better word, constitutive relations? Right now, you've showed the effect of radiation and plastic deformation giving rise. So, could we come up with a generalized idea for all fields? I mean, in some sense, I mean, the evolution of the free energy as a function of field. Could we look for some invariance or something, some commonalities that?
Yeah, that's a very good point. Originally, when we studied alloys under radiation and then alloys under severe plastic deformation, we saw those two situations as two different examples of driven or non-equilibrium systems, but two very distinct examples. The physical processes are very different. The way irradiation creates damage in an irradiated material is very different from the way dislocations may affect or modify the microstructure of an alloy. And so we were in fact surprised when we saw that, say, in copper silver, copper niobium, you tend to see almost the same or very similar microstructures in both environments. This being said, I mean, we don't have a good way, necessarily a good way to capture fully this similarities. There is one approach that that may provide a partial answer to your question. I mentioned that Georges Martin introduced this effective free energy here for capturing the evolution of these dynamical systems with competing dynamics. If you look at the first term here, if I absorb this gamma B into omega, it's as if I had an effective thermodynamic model with an effective heat of mixing, or you could just say keep the heat of mixing the way it is at an effective temperature. So Georges Martin developed a model of an effective temperature, and say, well, this is a simple maybe tool that will tell you under radiation or under severe plastic deformation, the state that the system will reach at steady state in that non-equilibrium environment at low temperature would be the same as if it had been operating at higher temperature at equilibrium. And you just have to look at the equilibrium phase diagram and it will predict the sequence of steady state. So the simple physical picture is that mixing here is essentially a source of entropy, and entropy is related to temperature, and by pouring or introducing disorder into the configurations, it's as if we were increasing an effective temperature.
Cool. So that's the key.
Yeah,
Is
this
this-
simple concept has its limitations. So, because there are certain things that you cannot. So, for instance, you might predict why precipitate will dissolve under plastic deformation or irradiation, because if you look at the phase diagram and raise the temperature high enough to cross the solubility limit, you will be in the single phase region. So that's consistent with dissolution, the disappearance of precipitates. However, there is no nanostructured microstructure in an equilibrium phase diagram. So self-organization cannot be captured by that effective temperature criterion. But there are a lot of already first effects that are captured by it. So.
Cool. Thank you. I think maybe Marat may have a question.
Yeah,
Okay.
sure. Yeah, go ahead,
Oh,
Marat.
no, I think he accidentally unmuted himself. But I assume, Pascal, you'll be open for more discussions
Sure.
if you have questions.
I'll be, indeed, yeah, I'd be delighted to interact with people separately or after the colloquium, or schedule a Zoom meeting or somewhere to.
Hi, Pascal. It's me, Venkat Manga.
Yeah.
University of Arizona.
Hey, hi. How are you doing, Venkat?
Doing good. I thought I would write a separate email asking this question, but this is about effective free energy. I would like to understand, has anyone, if you mentioned about the distribution functions, if there is an experimental effort trying to measure the distribution functions for such steady state, like the energy distribution of different atoms under steady state, and then use that distribution function in phenomenological models or models like whatever you were showing.
With the idea to see whether it makes a difference and whether we can use experiments maybe to infer what those distribution functions are. Yeah, that's a good question. The short answer is no, but every so often there are certain things that can be. So if I imagine you had in mind the case of alloys under radiation, but
yes.
Let me use the case of alloys under severe plastic deformation, because it's one case where we have an answer that fits a little bit what you said. This super diffusive mixing here, this rate at which plastic deformation randomizes a configuration. We expect it to be captured by the fact that if you precede the microstructure with precipitates and under conditions where there's no thermal diffusion, that the strain to dissolve those precipitates will scale linearly with the diameter, the initial diameter of those precipitates.
I see.
And it's a direct result from that super diffusive mixing and the equation that was introduced by Richardson, saying for that super diffusive mixing. So on the right hand side, we tested that numerically. So we used copper silver again. We did a heat treatment to start with different precipitate sizes. We used X-ray diffraction and atom probe to identify the strain that was required to dissolve those precipitates. So we obtained the strain by performing high pressure torsion testing experiments, because then you can quantify the strain. And then this super diffusive mixing, this is the equation one, should have been the dashed line here. And so experimentally we measured that straight line. So it is linear, but the slope is maybe 60% or 70% of the expected slope. But it is the right functional dependence. So I think you can say maybe there's an effective coefficient, or not all dislocations contribute equally. But it seems that one case where this kind of distribution or mixing law was tested by experiments. So.
I see. Thank you. Thank you for the nice talk.
Nice to talk to you, Venkat, by the way.
Thank you. Bye.
All right, do we have more questions? I can ask one more if no one else has, and then we can probably close. So yeah, Pascal, I know that you talked about this, but can you briefly again summarize how do we include the incident radiation, the irradiation into typically in phase field models?
Yes. So what we so if I go back to that slide 11 or 12 or a little bit later. So this is in part what we do. So we know that what we want is to have this mixing term in orange here, where we and it's just a balance equation. It's just keeping track of all the atoms or the B atoms that are located at R and left because of a recoil event, and all the atoms that were B atoms that were at side R prime that were recoiled into R because of a recoil event. And so what we can determine the distribution function by dissimulations. It's probably what I think what Venkat was saying, and we've seen cases where it's exponential somewhere. This part of it is Gaussian. And so but in phase field modeling, it is difficult to deal with these non-local terms, as probably you know too well.
Yes.
And so what we decided to try is to see whether we can replace this compact non-local term with maybe more terms, but they're all local. And this is what happens when we went from the first line to the second line. So here what we did is we replaced this convolution product. It's neat and compact, but it'd be difficult to handle with the phase field model. It'd be easy to do that in Fourier in reciprocal space, right?
Yes.
But then there are issues, so we cannot use that with Moose, at least not that I know, because it's a FEM implementation of a phase field model, and there are at least there are issues or complications, and so what we did is that we did a Fourier transform of that expression, then a Taylor expansion of that Fourier transform. So for Gaussian, you end up with a Gaussian in reciprocal space, and then we have we truncated. So each term of that Gaussian expansion, when you transform back into real space, gives you a differential operator on the composition that with power 2, 4, 6, and so on.
How do you, by the way, calculate the mobility? So is the mobility the diffusional mobility, or is it something that is also impacted by the momentum imparted by the flux?
That's a very good point, is that usually we end up having to derive that mobility from other models in general, because mobility here is affected by the concentration of point defects, and under radiation you create point defects, so the mobility goes up. It's known as radiation enhanced diffusion. So the mobility, that's why it has a superscript irradiation here to capture that it is modified by irradiation. And so it becomes challenging or complicated. In the model that Gabriel is implementing, here it's much easier in a sense that in addition to concentration, we also include a field for vacancies and a field for interstitials. So we have, so there are those three fields, and then there's one field for the dislocation array. And so we create point defects in a way that's reasonable based on everything that's known in the field of creation of point defects, but in a continuum sense, and assuming that those point defects are isolated. Yeah. There are limitations to that. We know that in some cases point defect start forming clusters like di vacancies, tri vacancies, and potentially we would want to include those defect clusters, but it becomes complicated because, as you realize quickly, if you describe those objects or defects by fields and they form clusters, this is not a good problem for phase field modeling. Right?
Yeah, correct. I agree. Yeah. So yeah, I think we are past the time, so I think we'll have to bring this to a close. But nevertheless, I have still so many questions, and I'm sure our audience as well, including Krishna and others at UFA. So we can keep this discussion going on email. I'm sure many of us are going to actually reach out to you and for more discussion. And maybe you can give us we can talk in groups, or I'm happy to collaborate with your way it is possible. So yeah, with that, let's close this. And thank you again for.
Very good. Thank you so much, everyone, and nice to see your question and you and Venkat and different people I know there too. Okay,
Thank
have a
you,
good day.
Bye.
Thank you. Have a nice day.
You too.
Enjoy the sun. Yeah.
Bye.